Hey guys, so this will be y'all's CE 3303 Discrete Time Signals and Systems Exam 2 review. This exam will cover everything involved in the frequency domain. All right, exam 1 was the time domain. Y'all are done with that. Now it's frequency domain. I will break this into a part 1 and a part 2 because y'all have so much material being covered on this exam. So this is the agenda for part 1, and part 2 will be released shortly after this. For part 1, we're going to go through the Z transform first, and we'll talk about the summation formula for it, Z-transform pairs and properties, and of course the inverse Z-transform. From there, we'll go into the transfer function, what it is, what it means, why it's important. We'll learn how to solve DT-LTI systems using the transfer function, and of course, how to determine if a system is stable using a transfer function. And these right here, these first two topics, I put a star by them because I will have plenty of examples for those, and these are what's very important for your test in terms of actual examples. 3 and 4 are going to be basically conceptual stuff only. I'll cover the Fourier series, Fourier transform, and sampling, and this is really for your better understanding of what some of the later stuff in the course is covering, mainly context for what DTFT is. I won't have any examples because I don't believe you'll have any examples of these on your test. But for those who do really enjoy this class and want to understand more, that's what this section will be for. If not, if you're just trying to understand the math so you can get through the test, feel free to skip this part. Like I said, 3 and 4 right here are going to be conceptual only. It's for your understanding, where we'll cover Fourier series, Fourier transform, how that leads into TFT, and then sampling will cover Shannon's sampling theorem, the Nyquist frequency, what aliasing is, and how sampling leads directly into DTFT as well. Okay, so let's go ahead and get started with Z transform. Okay, so Z transform, I'm going to go ahead and give the mathematical definition first, and then I'll explain what it is. But the Z transform is simply taking our time domain function, x of n, okay, and we transform it using a Z transform, and it becomes a function of z, x of z, and we define that function as the summation from n is equal to 0 to infinity, x of n times z raised to the negative n, okay? Where z is a complex number, okay? So z is equal to a magnitude r times e raised to the j omega, okay? As far as Z transform right now goes, you don't have to worry too much about this. You'll just be dealing with Z, not necessarily its complex form. But when we get to stability and DTFT, I want you guys to realize that Z is a complex exponential because it'll come into play later. So what exactly is the Z transform telling us? So the Z transform is simply a mathematical transformation from the time domain, denoted by x of n, okay, to the complex frequency domain. And there's actually, I guess, two domains we'll be talking about when it comes to frequency, especially when we get to DTFT. For now, this is denoted by x of z. So really, until we get to DTFT, I personally like calling this the z domain because it's more mathematical than anything, whereas when you think of frequency, you think of real world connotations. We'll get more into that into the DTFT, discrete time Fourier transform. For now, we'll just call it the Z domain. And what this is actually saying, because I know this still seems pretty generic, is basically in the time domain, we had annoying difference equations, right? Our our DT-LTI systems, they were modeled by difference equations, and we had to do annoying stuff like characteristic solution, particular solution to find, solve our system. Or we could do convolution, which is pretty tedious, but it's a lot better than doing characteristic and particular solution. The point of the Z-transform is we basically apply this mathematical transformation to map our system from the time domain to the Z domain, because in the Z domain, these difference equations now become algebraic equations. So we apply this Z transform onto our time domain signal, and it becomes a new Z domain signal. And the purpose of this transform, which is defined here, is to basically turn all of our difference equations into algebraic equations to make it so much easier to work with. So the purpose really is just to ease our pain when it comes to solving these DT-LTI systems. We simply take our DT-LTI system in the time domain, apply the Z transform. Now we're messing with algebraic equations, solve it in the Z domain, and then use the inverse Z transform to go back to the time domain, and it makes the math a lot easier. And of course, there's much more applications of the Z transform than that, especially involving the transfer function, but I'll get to that once we get to the transfer function. For now, just recognize Z transform as a way of easing our pain for solving these different systems. Instead of using difference equations, now we can just use algebraic equations, and it makes our math a lot easier. Okay. And of course, this is very important right here. This is our definition for the Z transform. Okay. So let's do a quick example of using that sum. Okay, we can simply do, say, x of n is equal to 1. We'll do 2 and then 4. And we'll start 0 right here. So if we recall, x of z is equal to the summation from n is equal to 0 to infinity, x of n e to the minus j. I'm sorry, I was writing DTFT. X of n z to the negative n. Okay. So let's go ahead and map this time domain signal into the Z domain by using this formula. So x of z is going to be x of 0, z to the 0th power, right? Plus x of 1, z to the -1 power, right? N is 1, and we just have the negative in the exponent right there. Plus x of 2, z to the -2 power. So if we substitute our x of 0, x of 1, and x of 2 in, we'll have 1 plus 2z to the -1 plus 4z to the -2. And that's it. One way of simplifying this, and what you will do a lot more than likely, is actually try to get rid of these negative exponents. So to do that, you just take your highest power. For us, it's 2, and you multiply it by z squared over z squared, which is just 1. And this will get rid of all your negative exponents. So we'll have x of z is equal to z squared plus 2z plus 4. Okay, and this is our Z transform. And remember, this is just our signal represented differently. Okay, instead of representing it in the time domain using n, we're representing it in the Z domain using z. And we haven't got into systems in the Z transform yet. This is just pure math, learning how to go from these different domains. Once we get to transfer function, you'll see how this applies to solving systems. And that's where what I talked about earlier, where our systems become algebraic equations instead of difference equations, and it makes our life easier. For now, we're just practicing pure math, transforming one signal from the time domain to the Z domain. Okay. I probably won't use another example for this one, because the summation is pretty straightforward. Just follow the formula and you should be fine. But what we should talk about is definitely Z-transform pairs. Okay. So Z-transform pairs and properties. So more often than not, you will not be using the Z-transform summation. You'll instead be using Z-transform pairs that are predefined for you by mathematicians. So if I come and open the textbook, let's actually change this. Okay, and we go to Z-transform. It's convolution, almost there. Here's the Z-transform. Okay, so what Z-transform pairs are is people, mathematicians, have gone and done this summation on plenty of known and common signals, such as our delta function, our delayed delta function, step function, exponential, stuff like that, sinusoids, and they've used that summation to come up with what the Z-transform would actually look like. And this is what we get, our Z-transform pairs. So for our basic signals that we use a lot, we already have the Z-transform laid out for us. I believe you'll get a cheat sheet on the exam, so I would definitely suggest writing this on y'all's cheat sheet, this table, because you'll use it a lot. But yeah, so Z-transform pairs are simply a known signal such as a to the n u of n, and its Z-transform counterpart is z over z minus a. Okay, a being what's right here in that exponential. And for properties, and we'll do a few examples, you have all of these properties that I'm sure you've seen plenty during your time in class of Z transforms. Basically, the way questions will usually be phrased is you get a time domain signal and you try to see, okay, it looks something like maybe sine, but it's a little different. You would use these properties to try to get it as close to the sine time domain signal as possible and use the Z transform on it. So let's do an example. Let's do okay, this one's pretty straightforward. So we're given a signal x of n is equal to n a to the n u of n. Okay, so this is a very generic signal. We're not given what a is. But if you'll notice, this signal n a to the n u of n is actually on your table, I believe. Yeah, right here. So we're actually just simply going to be proving this transform pair. Let's say we're given this, given that the Z transform of n u of n is equal to z to z minus 1 squared. Okay, so given this, the Z transform of n u to the n, I'm sorry, n u of n is equal to z over z minus 1 squared, find the Z transform of n a to the n u of n. Okay, and so this is going to be the same procedure that you follow usually when you're doing a Z transform. You're going to identify the function you're using. In our case, it's this one given. Okay. 2, you're going to find a property that basically, we'll call it, connects the given function to our desired solution. And then we will utilize that property. So what I mean by this is we're already given the z transform of n u of n is equal to z over z minus 1 squared. But we're trying to find n a to the n u of n. All right, well, how do we do that? Well, we come over to our properties table, okay, and we see there's a property for multiplication by a to the n. So any function x of n, u of n, remember having that u of n there just basically means that it's a causal signal. If we multiply this function by a to the n, well, the z transform is the exact same thing, is the exact z transform of x of n, but instead of z, we're just going to substitute for z minus a. So what this means is if we consider this whole thing to be x of n, then this right here is a to the n x of n. So then this right here is x of z. So the z transform we're trying to find is x of z over a. And this x of z over a is going to be our z transform for a to the n x of n. So if we take that, so the z transform we're given is z over z minus 1 squared. To find the z transform of this function right here, we're simply going to substitute z over a for z. So if we do that, we get z over a over z over a minus 1 squared. Okay, and to simplify that, we'll simply multiply a squared over a squared and we will get z times a. Okay. And if I factor this out right here, I'm sorry, if I expand it, I will get z over a minus 1 times z over a minus 1 times a squared. And that gives me, I'm going to flip this az over, I'm just spoiling, z squared over a squared minus z over a minus z over a, so it's minus 2z over a plus 1 all times a squared. So if I deliver that a squared through, I should get az over z squared minus 2az plus a squared. And I simplify that, I get az over z minus a squared. There's my answer. And we can double check with the transform table. That n, a to the n u of n, is in fact az over z minus a squared. Okay. So now let's go into inverse z transform. So the procedure for doing the inverse z transform, like I said earlier, is called partial fraction expansion. Okay. And before I get to partial fraction expansion, there's a few terms that you guys should know. So zeros are the terms that make the function equal 0, and poles are the terms that make function go off to infinity. Okay. So we'll be using poles a lot. Unfortunately, zeros are denoted by z. Just know if I have a little subscript by z, it's a 0, not the actual variable z in our z transform. And poles are denoted by p. Okay. And they have a subscript because there's multiple z's, multiple zeros, and multiple poles. And we'll talk a lot more about zeros and poles when we get to the transfer function. But the reason it's important is for this in particular. This is going to be the procedure. If we have our, let's just take this x prime of z, and x prime of z is simply equal to our z transform x of z divided by z. Okay, this is the first step in doing inverse z transform. We take our z transform, we divide it by z, and we'll call that x prime of z. Okay. Any z signal can be represented as a sum from I is equal to 1 to some upper bound of a constant ai over z minus a pole. Okay. So what this is saying is it could be something like 2 over z minus 1 plus 3 over z minus 2. Okay. So this would be for our I equals 1 term. This would be for our I equals 2 term. So that means our upper bound n is equal to 2. So this right here is a sub 1. This right here is a sub 2. And it just so happens, I'm not going to go into the math, but these z transforms can be represented by these I guess partial fractions right here, a summation of these. The reason that's important is we can utilize that property to do our inverse z transform. So for the first step is taking your z transform, dividing it by z, and calling it x prime of z. Okay. The next step is finding these a sub i's. Okay. These are our unknowns. The poles are going to be known to us, and you'll see when we do an example, but our unknowns are these a sub i's. So to find our a sub I, say a sub I is equal to x prime of z times z minus our pole sub I, and we're going to evaluate this function at z is equal to that pole. This will get us our a sub z. Okay. And once we find all of these a sub i's, well, then we can determine this equation right here and get it into something more tangible, such as this right here with the example I showed you. And once we do that, we'll just revert back to our x of z. So x of z is equal to x prime of z times z. And remember, x prime of z we said was equal to this summation is equal to 1 to some upper limit n a sub I over z minus pi. And because we're multiplying by z, we'll just have that. We'll add z right there. So a sub I times z over z minus pi. And what you notice is if we go to our z transform pairs, we actually have something for that. We have a to the n u of n. We z transform that, we get z over z minus a. Okay. If we come over here, we're going to take advantage of that property. So I'll say a times our pole raised to the n u of n. Okay. So if we look at the z transform table, this pole is basically the same thing as our lowercase a to the n u of n. Okay. And then this is just some coefficient. The z transform of that is our coefficient times z over z minus p, just like we saw in the z transform table. And so this is how we do inverse z transform. utilize the partial fraction expansion to get a summation like this. And then we just use the fact that the z transform of all these types of partial fractions is a times z over z minus p. And we'll have a p to the n u of n. So if I take this example up here, let's say we got our x of z was equal to 2 over z minus 1 plus 3 over z minus 2. We're utilizing this right here. We can say that x of n is equal to 2. This is p. Remember, it's z minus, so p is positive 1. Okay, so p raised to the n, or I'm sorry, 1 raised to the n is just 1. So we have 2 u of n, okay, plus 3 times 2 raised to the n. This is our p u of n. Okay. Let's do a few examples. Let's do this example right here. So compute the inverse z transform of z plus 3 to z plus 1. Okay, so this is our x of z right now, and we need to get to x of n. So the first thing we do is we get x prime of z, which is equal to x of z, x of z divided by z. So we take z plus 3 over z plus 1, and we multiply it by 1 over z. Then we get z plus... My bad. Let me do a more complex example. Let's actually take the inverse z transform of 1 over z plus 1 times z plus 2. Yeah, that'll be better. Okay. So our x of z over z, same thing. We have x of z, which is 1 over z plus 1 times z plus 2. We divide it by z, which is the same thing as multiplying by 1 over z. We get 1 over z times z plus 1 times z plus 2. Okay. And so now this x prime of z, 1 over z times z plus 1 times z plus 2, is equal to, we just set this up, you take each of these terms and you put them underneath the coefficient. So you say a1 over z plus a2 over z plus 1 plus a3 over z plus 2. Okay, that's what we have up here. This summation, not this one, of a sub I over z minus our poles. Okay, so in this case, our poles, let's go ahead and identify our poles. So p sub 1 is equal to 0. Right here, p sub 2 is equal to -1. And here p sub 3 is equal to -2. These are our poles. Okay, so let's continue this. To actually find a sub 1, we take x prime of z and we multiply it by the term that's underneath it. So in this case, we have z, and we evaluate it at that pole. So our pole is equal to 0, right? So we evaluate for z is equal to 0. So if we do that, remember this is our x prime of z up here. So if we multiply by z, the z will simply cancel out at the bottom, so we're left with 1 over z plus 1 times z plus 2. And we evaluate that at z is equal to 0. So what does that leave us with? That just leaves us with 1 over 1 times 2, which is just 1/2. right? Because then we get 1 right here, 0 plus 1, and then 0 plus 2, we get 2, and we got 1/2. All right, now let's find our a sub 2. To get a sub 2, we multiply x prime of z times z minus our pole. And this is right here, these terms are z minus our pole. So if you notice, this is z minus 0, this is z minus -1, which is z plus 1. We do z plus 1, and we'll evaluate it at our pole. So z is equal to -1. So that gets us 1 over z times z plus 2, evaluated at z is equal to -1. And we get 1 over -1 times -1 plus 2 is just -1. So we get, I'm sorry, -1 plus 2 is +1. So we get 1 over -1, which will just get us -1. Okay. So now let's find our third coefficient, a sub 3 is equal to x prime of z times z plus 2. Right, now we're using this one. Our pole is -2. Got to evaluate at z is equal to -2. So we'll get 1 over z times z plus 1. Evaluate it at z is equal to -2. We get 1 over -2 times -2 plus 1, which this right here is just -1. So we get 1/2. So looking up here, we have x prime of z. Remember, this is not x of z, this is x prime of z. It is equal to 1/2 over z minus 1 over z plus 1 plus 1/2 over z plus 2. So now that we've got that, we can say x of z is equal to x prime of z times z, which is equal to 1/2, just 1/2, yeah, the z's cancel out, minus z over z plus 1 plus 1/2 z plus 2. And so now we just simply take the inverse z transform of these, which all of these have pairs. So this is simply a constant. So what's our pair for a constant? It's just the delta function, right? So this is going to be, say, x of n is equal to the inverse z transform of x prime of z. I'm sorry, not x prime of z. X of z. And we take this inverse z transform of all of these using our table. So the inverse z transform of a constant is just that constant times the delta function. We look here. We have 1 is the z transform of the delta function. So if we have 1/2 times the delta function, our z transform will just be 1/2, which is what we do here. Minus z over z plus 1. If we look at our table, z over z minus a. So we can say our a is a -1. So we'll have our time domain function -1 to the n u of n. So we'll have minus a -1 to the n u of n. Okay. Plus 1/2, that's just our constant, z over z plus 2. So this is the same z transform as earlier. A to the n u of n is z over z minus a, where this time our a is -2. So of 1/2 times -2 raised to the n u of n. This is our time domain signal. Pretty simple. And now there's two other caveats to the inverse Z transform. The first being is repeated poles. So let me see if I can find an example on that one. Okay. Let's say we have 1 over, let me say this is another example. Let's say we have 1 over z squared times z plus 1. Okay, this is, and we want to find the time domain signal for this z signal. So we need to do the inverse z transform. So we can say x prime of z is equal to x of z over z. I'm sorry, let's actually just make this 1 over z times z plus 1. So now our x prime of z is equal to x of z over z. So we'll have 1 over z squared times z plus 1. We simply multiplied times 1 over z to our x of z. And so now the way we represent this in our partial fraction expansion is a1 is going to be our first term, z squared, a1 over z squared. But when we move on to the next one, we have to basically keep decreasing the power of this until we get to just 1. So for our case, it'll be a1 over z squared plus a2 over z. And now that we're at just z, so power of 1, we can move on to the next term, which is z plus 1. So a3 over z plus 1. Okay. So the way we do this is almost the same thing, just with a little bit different. So to solve this a1, it's the exact same thing we did before. a1 is equal to x prime of z times z squared, evaluated at our pole. Pole's still going to be 0. Okay. And by the way, the pole is just what makes this denominator term equal to 0. So obviously here it would be 0 is our pole. Our pole 2 is also 0. And here pole 3 is -1, because -1 plus 1 will get you 0, and now we have 0 in the denominator. As you can see that, I mean, if you have 0 in the denominator, that drives you to infinity. And that's why. So we've got x prime of z times z squared evaluated at z is equal to 0. So here's our x prime of z. So we got 1 over z plus 1 because we multiplied by z squared. We'll evaluate that at z is equal to 0, and we get 1. Now for a2, we do not do x prime of z times z and evaluate that at 0. We don't do that, okay? Make sure not to do that. What we do is we take our previous term, which is x prime of z times z squared, and we actually take the derivative of it with respect to z, and then evaluate that at z is equal to 0. So remember, this term right here, x prime of z times z squared, is this right here, 1 over z plus 1. Let me grab my charger real quick because my computer's about to die. So what we need to do is take the derivative of this function right here. So you guys are definitely going to have to remember this for the exam. The quotient derivative rule. It's been a while since I've had to use it. So the quotient derivative rule is simply if we have u over v, the derivative of that. So just say that. The derivative of u over v is simply u prime times v minus u times v prime over v squared. So make sure you guys remember that. So if we do this example up here, we'll take the derivative. So u prime is simply of the derivative of 1 is just 1, or no? Yes. Okay, my bad. Yeah, so the derivative of a constant is just 0. So we'll just have 0, not, yeah, we'll just have 0 there. Minus, and then we'll do u and then v prime, so that's 1 times 1 over z plus 1 squared. So we'll just have -1 over z plus 1 squared. Okay. So this is what we evaluate at z is equal to 0. So if we do that, we'll get -1 over 1 squared, which of course is just going to be -1. Take A3. A3 is z plus 1. So we take x prime of z times z plus 1, evaluate at z is equal to -1. We'll have 1 over z squared, evaluate at z is equal to -1. We'll go ahead and get 1 over 1. So we just get 1 for that. So now we've got x prime of z is equal to 1 over, right? Yeah, we have 1 there. 1 over z squared minus 1 over z plus 1 over z plus 1. So then x of z is equal to x prime of z times z. So we'll get z over z squared minus z over z, z over z plus 1. So we get 1 over z squared, I'm sorry, 1 over z minus 1 plus z over z plus 1. So we'll have here is z to the -1 minus 1 plus z over z plus 1. We take the inverse z transforms of each of those. Z to the -1 is just delta of n plus 1. Okay. Minus delta n plus -1 raised to the n u(n). That's our answer. And where this comes, delta of n plus 1 is right here. We got z to the -m. The inverse z transform of that is delta n minus m. So for in this case, our m was I'm sorry, hold on. I believe it actually should be -1. Yeah. Because our m right here is, this is our m, it's 1. Okay. So if we come over here, the z transform of z to the -1 in our case would be delta of n minus 1. And that's what we have right here. Now let's look at, I'm not going to complete this example, but I do need to show you what happens if you get complex conjugates for your poles. So let's say we have this z transform. X of z is equal to z e to the j theta over z minus a plus c e to the minus j theta z minus a conjugate. Oh, wait, hold on. No, I'm sorry, not that, definitely not that. We got x of z is z squared minus 2z over z squared minus 2z plus 2. Okay. So first step is get your x prime of z. So remember to do that, you just divide by z. We've got z squared minus 2z times z squared minus 2z plus 2. Okay, so now let's factor this. We get z squared minus 2z over z times, and if you factor this, you'll actually get z minus 1 minus j, I believe. Yeah, and z minus 1 plus j. And that just comes from the quadratic formula. Yeah, so I can show that really quickly. So we'll have negative b, which is 2, plus or minus the square root of b squared, 4, minus 4 times a, 1, c, 2, divided by 2. We get 2 plus or minus negative 4 over 2, which would be 2 plus or minus 2j over 2, which is simply equal to 1 plus or minus j. Okay, so now our poles, pole 1 can be 1 minus j, pole 2 can be 1 plus j. That's what we do here. So this is, oh, let's do that. So this is actually pole 1, this is pole 2. This is pole 2. So we just did, yeah, z minus 1 minus j, which is z minus 1 minus, or plus j. And then z minus 1 minus j, 1 plus j. No. Yeah, z minus 1 minus j. Okay. So now if we take this, we've got x prime of z is equal to z squared minus 2z over z. We've got three terms. We've got z, and we've got z minus 1 minus j. Okay. And then we've got z minus 1 plus j. Okay. And so we're going to have a1 over z Yeah, so we'll have a1 over z, then we'll have a2 over z minus 1 minus j. Okay. And then this is the thing to note, a3 is simply, I'm sorry, a3 is just the complex conjugate of a2. Okay, so once you find your a2, you've got your a3. I'm not going to finish this example because I believe when we get to transfer function, we'll be able to practice this. But this is just the important thing to note, is that when you have these complex poles, you simply find a2 or a1, whatever it may be, and the next constant is the conjugate of that. Okay, so you will more than likely have complex numbers for these a's when you have complex poles. But yeah, I don't want to linger too much on that. I think we need to get to transfer function now. So let's do that. transfer function. Okay. So our transfer function is, we call it h of z, and we define it as y of z over x of z. Okay. So if I have some function, some signal x of n, put it through system, I get y of n, right? And y of n is defined as y of n is equal to the convolution of x of n and h of n, the impulse response, right? So let's z transform this whole thing. So if I just take the z transform of x of n, I'll get x of z. Put it through some system. Okay. I take the z transform of y of n, I'll get y of z. Okay. I'm not going to go through the whole proof for this, but the purpose of the z transform is that y of z is equal to our transfer function multiplied by x of z. And this is what I was talking about at the start of the review, where the purpose of the z transform is turning difference equations into algebraic equations. It makes our life easier. Because the thing to note about the z domain and the frequency domain, same things basically, is that convolution in time domain equates to multiplication in the frequency domain. Okay, so what you actually notice here is x of z is the z transform of x of n, and our transfer function is actually the z transform of our impulse response. Okay, so another definition for our h of z is the z transform of our impulse response. Okay. And you're going to hear me say this a lot, but the importance of the transfer function is that it characterizes our system. Okay. It tells you everything about the system. I'll show you how. So firstly, let's see. The main thing to note about the transfer function is this right here. This is how we will solve DT-LTI systems. Okay, you need to remember that y of z is equal to our transfer function times x of z. So let's define our transfer function mathematically. I'm sure you guys remember this. A general form for a difference equation is y of n is k is equal to 1 to the n a sub k y of n minus k. Let me actually put that in brackets. Plus k is equal to 0 to L b sub k x with n minus k. Okay, remember this is just a general form of a difference equation. Okay, this is just showing our, remember our output y terms, and these are our input x terms. So the way we define a transfer function given a difference equation is h of z is equal to k is equal to 0 to L b sub k z to the minus k over 1 minus the summation of k is equal to 1 to n a sub k z to the minus k. Okay, so what this means is we're just taking all the coefficients of our input terms, okay, and we're basically applying that z transform summation I showed earlier. We'll take b sub k z to the minus k. And on the denominator, we'll do 1 minus all of our output terms coefficients and multiply them by z to the minus k, whatever k may be. Okay. So the best way to really understand that is just to do a quick example. So, example here, y of n is equal to negative 0.3 y of n minus 1 plus 3 x of n. Let's see if I can find a better example. Oh, okay, yeah, I wrote that wrong. Okay, so y of n is equal to negative 0.3 y of n minus 1 plus 3 x of n. Okay, this is our system represented as a difference equation. Our input signal is going to be x of n is equal to 4 times 0.2 raised to the n u of n, and we need to find out what our output signal is. Okay, so we're going to use this summation up here to figure out what our transfer function is, h of z. So h of z is equal to the sum of our x term coefficients times z to the minus k. So we've got right here, this will be b sub 0. So we're going to have b sub 0, which is 3 times z to the negative k, k being 0 right now, so we just have 3. And then we don't have any more x terms. If we did, say we had like plus 4 x of n minus 1, then up here we would have plus 4z to the negative 1. Okay. Now for the terms on the bottom, we'll do 1 and then minus our a sub k's. And so for this, we'll have 1 minus a negative 0.3, so we'll have positive 0.3. And this one will be z to the minus 1, because notice here we actually start at 1 at k is equal to 1. So at the top we start at k is equal to 0. So we do have z to the minus 1. Okay, and that's our transfer function. And so, like I said before, let's get rid of these negative exponents. So if we multiply by z over z, we'll get 3z over z minus 0.3. I'm sorry, this should definitely be a plus. Remember, we did 1 minus negative 0.3, so it should be 1 plus 0.3. We've got this here. So now, remember, y of z is simply equal to x of z times h of z. So we've got h of z, cool. Now we need to find x of z. And x of z is just going to be the z transform of our input signal x of n. So just this function look familiar from the z transform table? Should. If we think about it, we've got some coefficient, big A. Okay. We've got a, little a raised to the n, u of n. Come here, a to the n u of n is z over z minus a. So our x of z is simply 4z over z minus 0.2. Okay. So now let's figure out what y of z is. Y of z is equal to x of z times h of z. Okay. So that's going to be our x of z was 4z over z minus 0.2 times h of z, 3z over z plus 0.3. So let's multiply this out. We will get 12z squared over z minus 0.2 times z plus 0.3. And let's leave it like that. So this is our y of z. But we want y of n, right? We want to be in the time domain. So we need to go ahead and do inverse Z transform. The way we do that is how we did it before, using partial fraction expansion. Remember, the first step is always y prime of z. And we take y of z and divide it by z. So we'll get 12z squared over z times z minus 0.2 times z plus 0.3. Okay. So from here, we'll have, remember, a1 over z plus a2 over z minus 0.2 plus a3 z plus 0.3. Cool. So now let's find our a1. A1 is equal to y prime of z times z evaluated at our pole. Pole in this case is z is equal to 0. So that'll get us 12z squared over z minus 0.2 times z plus 0.3 evaluated at z is equal to 0. So we've got I believe we get 0 here. Oh, I'm so sorry, my bad. Okay, so I'm sure if this was live and I wasn't recording, you guys would have caught this. But we've got z squared and we're dividing by z, right? So this square will cancel out and this z right here. So what we should actually have here is 12z, I believe. And so, actually, come back over here. Now we actually have a1 over z minus 0.2 plus a2 over z plus 0.3. Okay, the z is gone, so we don't need that term anymore. So let's find our a1. We've got y prime of z times c minus 0.2. And this is going to be evaluated at z is equal to 0.2. Right, that'll make that term go to 0. So that should give us 12z over z plus 0.3 evaluated at z is equal to 0.2. So what we get from that is 12 times 0.2 over 0.2 plus 0.3. That gives you, some calculations, 12 times 0.2 is equal to 2.4 divided by 0.2 plus 0.3, 0.5. So 2.4 divided by 0.5 gives you 4.8. Okay. Let's do A2. A2 is y prime of z times z plus 0.3 evaluated at z is equal to negative 0.3. That'll get us 12z over z minus 0.2 evaluated at z is equal to 0.3. So that'll get us 12 times, I'm sorry, evaluated at z is equal to negative 0.3. So 12 times negative 0.3 over negative 0.3 minus 0.2. So if we do some calculations, 12 times negative 0.3 gives us 3.6 divided by negative 0.5. We get 7.2. Okay. So now we've got y prime of z is equal to 4.8 over z minus 0.2 plus 7.2 over z plus 0.3. Okay, so then y of z is equal to 4.8z. Remember, just multiplying z all the way through over z minus 0.2 plus 7.2 z over z plus 0.3. So we take the inverse z transform of each of these. We get y of n is equal to 4.8, and the z transform of z over z minus 2, minus 0.2 is 0.2 raised to the n u of n plus 7.2. We take the z transform of this. We've got negative 0.3 raised to the n u of n. And that's how we solve DT-LTI systems using z transform and the transfer function. So I'm going to write steps for that, general steps. So to solve DT-LTI, the first step is find your transfer function h of z and transform your input signal x of z. Second step is multiply those two to get y of z. Y of z is equal to h of z times x of z. Okay. Third step is use inverse z transform on y of z. Lastly, by doing that, you obtain y of n, and you're done. So these are your 4 steps to using z transform to find the output of your system y of n. Okay. So the next thing is stability. And this involves the transfer function. So bibliostability. So we recognize that our transfer function can be represented in quite a few ways. H of z can be y of z over x of z. It can be the z transform of our impulse response. Okay. And lastly, it can be some constant c times, and this is product. Okay, this isn't pi, this just means we're multiplying all of these terms. Z minus zi, the product, I'm going to put 1, z minus pi. Okay. So remember, these zi's are just zeros. And these pi's right here are poles. Okay, so there's 3 ways we can represent our transfer function, and this is what I mean by it characterizes our system. It tells us literally everything about our system. It tells us the output over the input, the ratio of the output over the input. From the transfer function, we can actually figure out the impulse response, which is very important to systems. And lastly, we can actually represent the transfer function as a product of z minus zeros divided by a product of z minus poles. And the reason this is so important is poles actually tell us if the system is stable or not. And what I mean by stable is if we put an input into the system, is the system going to converge to a number or is it going to diverge to infinity? So basically, if I put some signal x of n through a system, and I get some y of n function out, and the function I get is a decaying exponential, okay, clearly it converges to 0, right? That means this system is stable because it produces a stable output. But if I take an input and I put it through a system and I get output y of n out, and it gives me an increasing exponential, okay, that's clearly diverging to infinity. That means the system is unstable. It produces an unstable output. Okay, and I could have like a decaying sinusoid or expanding sinusoid. I can have plenty of things. The main thing to note is that if your output signal converges to a number, the system is stable. If your output signal diverges to infinity, the system is unstable. Okay, and the way the transfer function helps us determine if systems are stable or unstable is like this. If your poles, so pi, if your poles are less than 1, you're good. Your system is stable. However, your poles, and poles can be complex, so these are actually the magnitude. The magnitude of your poles are greater than or equal to 1. Your system is actually unstable. Okay. So this will better be illustrated with an example. So let's do that. Let's say I'm given a transfer function h of z, and it's equal to z minus 1 over z squared minus c plus 0.25. Okay. So let me factor this. I'll get z minus 1 over z minus 0.5 squared, but I'm just going to write it out. Okay. And so if you notice here, this form is actually the same thing as this form right here. So this tells us on top are zeros. This is z1 is equal to positive 1. Right over here, this will tell us our poles. Pole 1 is actually equal to pole 2, which are both equal to 0.5. If you notice, because our poles are equal to 0.5, they're actually less than 1, right? So pole is equal to pole 2, which are both less than 1. The magnitude of these, of course. So that tells us our system is stable. Okay. If these poles were greater than 1, it would tell us our system is unstable. So that's another huge application of the transfer function, is that just by looking at it, you can see the poles and zeros of a system, and that'll tell you whether or not a system is stable or not. Let's see. Yeah, okay. So that really, for the most part, concludes Z transform and transfer function. I know I said I was going to go into sampling and Fourier series and Fourier transform in this video, but I think it's already been, what, an hour? Yeah, so I'm going to go ahead and actually split this into 3 parts. So those of you who want to skip those Fourier transform and sampling parts, you can just skip part 2. But yeah, I'll go ahead and end this recording and get to part 2 here in a bit.